So let's look at this first problem here. The integral from 1 to 2 of x squared dx, and they want us to find it using the limit definition of the integral. So I wrote out this. The limit is n goes to infinity of the sum from k equals 1 to n of the height of your rectangle times the width of your rectangle. Right? We're just adding up areas of rectangles and taking the limit. And so then, I feel like my screen does not look super clear here. Sorry. Yeah. Okay. So then we just have to figure out for each rectangle what we're going to plug into our function. And so this is where you can either kind of, if you're using right endpoints, you can memorize this formula that the right endpoint of the kth subinterval is a plus k times delta x. Or we could draw it out. We say, oh, I'm starting at 1, I'm ending at 2. Each of my subintervals has a width of the length of 1 divided into n pieces. So this spot right here is 1 plus 1 over n. This spot right here is 1 plus 2 over n. Right? And if we're thinking about the function, maybe it looks like this, I don't know. And this is my first subinterval, and the right endpoint is 1 plus 1 over n. This is my second interval, and the second right endpoint is 1 plus 2 times 1 over n. And so for the kth subinterval, the right endpoint is 1 plus k over n. You're just taking your 1 and you're adding 1 over n k times, right? So you're adding 1 plus 1 over n k times. And that's what's getting plugged into the function, right? That's the x value you're plugging in to the function, which is x squared, which I totally didn't draw correctly, that's fine, to get the height. And the base of each rectangle is just 1 over n. All right. So then the rest of this is multiplying it out and applying the formulas. So we're going to multiply this out. We're going to get the limit as n goes to infinity of the sum from k equals 1 to n. If you multiply this out, it's going to be 1 plus 2k over n plus k squared over n squared. And then we're going to multiply that by 1 over n. So it's going to be equal to the limit n goes to infinity of the sum from k equals 1 to n of 1 over n plus 2k over n squared plus k squared over n cubed. What does it say x sub k is equal to? X sub k is equal to a plus k times delta x, which in this particular example is 1, right? A is 1, B is 2. So a is 1 plus k times the delta x is your 1 over n. And so then we're in good shape here because our powers of k are all 1 less than our powers of n, which is what we're always expecting to see. So then we're going to break this apart. We're going to write this as the limit as n goes to infinity. I'm going to break this into 3 separate sums, and I'm going to factor out all the constants that aren't k. So I'm going to write this as 1 over n times the sum from k equals 1 to n of 1 plus 2 over n squared times the sum from k equals 1 to n of k plus 1 over n cubed times the sum from k equals 1 to n of k squared. Right, so I broke this up into 3 different sums: the sum of 1 over n, the sum of 2k over n squared, and the sum of k squared over n cubed. And then factor out all the things that weren't k into the front of the sum. So then we can use the formulas. So this is equal to, so we know the sum from k equals 1 to n of 1 is just n. So the limit and you go to infinity of 1 over n times n plus 2 over n squared times the sum from k equals 1 to n of k is n times n plus 1 over 2. And then finally, the sum 1 over n cubed times the sum from k equals 1 to n of k squared, which is n times n plus 1 times 2n plus 1 all over 6. Then we can evaluate this limit. This is n over n is just 1, so you don't have to take the limit. This expression here, if you multiply it out, this is going to be 2n squared plus 2n all over 2n squared. And the limit is just 2 over 2, which is 1. This part here, if you multiply it out, you would get 2n cubed plus, I don't really care what the smaller terms are, but I will show you anyway. The smaller terms would be, let's see, 2n plus n is 3n squared, and then n times 1 times 1 is n all over 6, n cubed. The limit of this part is going to be 2 over 6. So our answer ends up being 1 plus 1 plus 1/3, which is 2 plus 1/3, which is 6/3 plus 1/3 is 7/3. And that's how you would do a problem like that. Daniel, what homework problem are you stuck on?
What's up, James? Yeah, it's let me see. I'm gonna pull it up just in case I don't want to make a mistake. It's computed an integral one, so it's pretty much U-substitution with plugging in the lower and upper bound.
Okay, we'll get there in a bit, but not just yet.
Oh, for sure. Yeah, take your time, James. It's fine.
Okay. So, are there any questions about this problem before we move on to other things?
I do have a question.
Yeah.
So for how you know how you got 2n squared plus 2n over 2n squared?
Yep.
You simplified that to 1 by
taking the limit. So what I'm really doing here, right, is right here, I'm taking the limit as n goes to infinity of 1 plus 2n squared plus 2n over 2n squared plus 2n cubed plus 3n squared plus n over 6n cubed.
Oh, so it'd be like infinity over infinity, and that's why it'd be 1?
Well, it's 1 in this case because the leading coefficients divide to 1. But for this part, the leading coefficients divide to 1/3.
Okay, yeah.
And again, we're using this rule back from 21a, that if you take the limit to infinity of a rational function, where the degree on top and the degree on the bottom are the same, in this case the degrees are both 2, in this case the degrees are both 3, if those degrees are the same, the limit to infinity is the quotient or fraction of the leading coefficients.
Okay, yeah, that makes sense.
Good.
Thank you.
Other questions about this? Sorry, so I should say in general, when you guys ask me to look at a particular homework problem, I'm happy to do that, but you should tell me whose class you're in, because I don't know off the top of my head who's in what class. So if I'm like, I can do problem 14 from that, I need to know whose class you're in. So let me know whose class you're in, and that goes for like when you're writing a discussion or a reflection or sending me a message. If you let me know whose class you're in, whether it's Schulten's or Morris, then I can definitely look at the problem you were asking me about. Yeah. So anyway, 1, 2, and so just as far as homework problems go, I assume that if you're asking about Schulten's, you're asking about homework assignment 2 that is due on April 15th. If you're asking about Morris, you're asking about homework assignment 3 that is due on April 18th. Because yeah, those are the ones that would make sense to ask about. So let's see, 1, 2, 3, 4, 5, 6. We can definitely look at that problem. I believe the person that asked me via direct message is asking about Schulten's because there aren't 14 problems in the other homework assignment. We will definitely get there as well, but we got a few things to do before that. No problem. It's really okay. But before, so I will have to say we got a few things to do before we get to either of those problems, because there's a couple things we want. So we really want to talk about the fundamental theorem of calculus for at least another minute or two. So I'll remind everybody, right, that we talked about last time how the derivative of the integral from a constant to x of some function of t dt is equal to f of x. So for example, really easily, the derivative of the integral from like 2 to x of, I don't know, let's say secant squared of t is equal to secant squared of x. Now you could actually show the work here if you wanted to. And actually, let's make it a little bit more interesting. Let's say this is, instead of being 2, let's say it's pi. So if I was actually going to do this the long way, which we don't usually do, but we can sometimes, we know the integral of secant squared is tangent. So we could also say, oh, look, this is equal to the derivative of, well, the integral of secant squared is tangent of t, evaluated from pi to x. And then if we plug in the x and the pi, we're going to get the derivative of tangent of x minus tangent of pi. The derivative of tangent of x is, of course, secant squared of x. And the derivative of tangent of pi, well, tangent of pi is a constant. I don't even care what it is. The derivative of a constant is 0. And you might wonder, why would you ever do it this way? And you'd be right to wonder that, like, you wouldn't do it this way. But if it's a little more complicated, it might make sense to. Meaning, let's look at this question. Let's look at the integral, the derivative of the integral from pi to x cubed of secant squared of t. And now let's do it the long way. So again, we know that the antiderivative of secant squared of t is tangent of t. So we're going to get the derivative of the antiderivative of secant squared, so tangent of t, evaluated between pi and now x cubed. Plug them in. So we still have the derivative of tangent of x cubed minus tangent of pi. The derivative of tangent of pi is still going to be 0, it's still a constant. But the derivative of tangent of x cubed, we now have to use the chain rule. The derivative of tangent of x cubed is going to be, well, derivative tangent of some stuff is secant squared of your stuff times the derivative of your stuff, which is 3x squared. So here's the more general version of the rule of the fundamental theorem of calculus part 1, which is the following. If you take the derivative of the integral from a to some function of x, let's call it g of x, of f of t dt, then the derivative of that is going to be, well, you're going to plug in the g of x, right, just like we plugged in x cubed here. We're going to get f of g of x, but then you have to multiply by the derivative of g of x, just like we did here. So in this particular problem, secant squared of t, that's your f of t, and x cubed, that's your g of x. And at the very end, we get f of g of x, right, secant squared of x cubed, times the derivative of g of x, which is 3x squared. So we can use this to find other things. For example, we can find, say, something like, I don't know, what's the derivative of the integral from -2 to x squared of sine of t dt? Could we do this the long way? Certainly. Do I want to do this the long way? Not really ever. Right? I want to use my time efficiently. As do you, right? You want to not work more than you really need to at a problem. You definitely want to work enough to understand it, but you don't be like, I'm doing extra work just for fun.
So James, you're pretty much saying the long way is f of b minus f of a, then doing all these little, every little step.
Right.
Much.
Yeah. The long way. Well, and so I'll do another problem and then we'll talk about So whereas the short way is just be like, I'm going to plug in x squared for every instance of t. So I'm going to get sine of x squared times the derivative of x squared. Done. That's it. Now, for this problem, we could do it the long way, where you anti-differentiate this, you get negative cosine of t, you plug in the limits of integration, you get negative cosine of x squared minus cosine of -2. And then you differentiate that and you get exactly sine of x squared times the derivative of x squared. But the point here is that sometimes you can't integrate the function, right? If I said, what's the derivative of the integral from, I don't know, 5 to e to the x of what do I want to pick here? I don't know, something terrible like sine of x cubed. This function can't be anti-differentiated. There is no antiderivative of sine of x cubed. There's a lot of functions that don't have any antiderivatives, actually. We don't usually encounter them very often. But we don't need to know the antiderivative here because we're taking the derivative of the integral, and we know that the derivative of the integral is just the function you started with. But in this case, right, it's not just going to be sine. Oh, I made a mistake. It's not a big mistake. It's a notation mistake. If you got x's up here, you shouldn't have x's here. These should be t's. Sorry about that. It's an easy mistake to make.
So James, we're pretty much doing part 1 right now, right?
Right. This is the fundamental theorem part, fundamental theorem calculus part 1.
Okay. Yeah,
that's a more complicated version of it, where one of your limits of integration, instead of just being x, is a function of x.
Mm-hmm.
So here, the derivative of the integral from 5 to e to the x of sine t cubed is going to be sine of, I'm going to replace t with e to the x. It's going to be cubed. And then we're going to multiply by the derivative of the thing we just plugged in. And the derivative of e to the x is, e to the x. And then I would do one more thing. I would simplify this. E to the x cubed is e to the 3x. So this would be sine of e to the 3x times e to the x. You can't combine these because this is sine of e to the 3x, and then this is times e to the x outside of the sine function.
James, how would it be 3 to the x?
Say that one more time.
How would it be 3, like 3x, pretty much?
Because when you have a power to a power, we multiply those powers. So if you have, right? If you have like 2 to the 3rd to the 4th, that's really 2 to the 12th.
2 to the 12th. Oh, okay.
Same idea there.
Okay, thank you so much, James.
Really, what does this mean? This means e to the x times e to the x times e to the x.
Mm-hmm.
But then you can just say, oh, well, e to the x times e to the x is e to the 2x if you add the powers. Another e to the x is going to be e to the 3x because you add the powers.
Oh, for sure, James. Thank you.
You're welcome. Let's look at a couple more. What if we had, say, the derivative of the integral from, I don't know, let's pick something fun like the inverse sine of x to 6 of tangent of t. I don't want to be super. No, I don't. Just to do tangent of t. Okay, so let me ask you guys. When your thing with the variable is in the lower limit, what extra thing do we get?
Don't you have to put a negative? Like
right. So here's the way of showing more steps you can do this is you can say, oh yeah, this is the same as the integral of the negative of the integral from 6 to inverse sine. but we know that it's just going to change our normal answer from being positive to negative. So be like, oh, I know it's going to be negative of, and then I'm just going to do the usual thing. Tangent of, plug that in. And then we multiply by the derivative of the thing we just plugged in. And the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. Or you could take the extra step of writing this as the derivative of negative integral from 6 to inverse sine of x of tangent of t dt. But I don't think you need to do that. Questions about any of these so far?
Sorry, so for like cosine or our cosine, would it be negative, right? Instead of like 1 over, it would be negative.
Correct. The derivative of the arc cosine of x is the same as the derivative of the arc sine of x, except it's negative. So the derivative of the arc cosine is negative 1 over the square root of 1 minus x squared.
Okay.
And a good thing to know is that's actually true for all the inverse trig functions. So arc sine and arc cosine have the same derivative, except cosine is negative. Arc tangent and arc cotangent have the same derivative, except arc cotangent's derivative is negative. And arc secant and arc cosecant have the same derivative, except arc cosecant's derivative is negative.
Okay. Oh, that's cool.
Let's do a couple more. And then we'll move on to someone asked, there's a problem from, I think, Morris's worksheet that people asked about. I'm happy to talk about for a second. Let's look at something like this. Let's say our function is, I'm going to write it differently. Let's say our function is, I don't know, g of x is equal to the integral from, what do I got here? X squared to natural log of x of, what do I got? T over 1 plus t cubed dt. And I want to find the derivative of that. So you don't need to do this, but if you wanted to, you could write this as the integral from x squared to some constant. We don't really care what. You could pick anything. I'm going to pick 0 of our function plus the integral from 0 to the natural log of x of our function. And then you could rewrite this as, I'm going to actually write this one first. Hold on for a second. It's the integral from 0 to the natural log of x t over 1 plus t cubed dt minus, I'm going to change the order of the limits of integration, the integral from 0 to x squared of t over 1 plus t cubed. Okay, so now watch this. When I take the derivative of this, I'm just going to use my usual rule. I'm going to say that the derivative, okay, so for the first one, I'm going to plug in the function, the natural log of x. I'm going to get the natural log of x over 1 plus the natural log of x quantity cubed. Right, so you have to plug this in for every instance of your variable t. And then we're going to multiply by the derivative of the natural log of x, which is 1 over x, minus, same deal here. We're going to plug in x squared for each t. So I'm going to get x squared over 1 plus x squared cubed, which I should simplify to x to the 6th, times 2x. Or the way I really actually think about it is, you're just doing top minus bottom. You plug in natural log of, you plug in the top thing first, which is natural log of x, multiply by its derivative, then subtract. Then since the bottom thing is also a variable, plug that in, multiply by its derivative. So the very, very, very general formula for this kind of fundamental theorem of calculus part 1 is that the derivative of the integral from g of x to h of x of f of t dt is f of h of x times h prime of x minus f of g of x times g prime of x. Or basically plug in the top thing, multiply by its derivative, subtract, plug in the bottom thing, multiply by its derivative, you're done.
James, I have a quick question.
Go ahead.
So when we figured out like our first upper and lower bound x squared to x squared, the integral of 0 to x squared, how did we choose 0? Is it because we set x squared equal to 11?
You could pick anything. You could have picked 10 and nothing changes.
Oh, okay.
So it could be any constant. Literally anything is fair game. The only thing you might technically have to worry about is if, I guess in this particular problem, if you picked -1, it would be an issue. Not really, but because if you plug in -1, this function's undefined there. But,
yeah.
but really, you can pick anything.
Okay, thank you, James.
Welcome. So let me ask. So should I do more of this, or are we good? Are we good with the fundamental theorem calculus? Like you just take the derivative of the integral, you get the function you started with.
That's for only the first part, right? Again, it's just
yeah, that's the first part. That, and then the second part of the fundamental theorem calculus, which we'll definitely talk about today, is the evaluation theorem. It just says to find the definite integral, you anti-differentiate and you plug your limits in the equation. Yeah. Let me look at one more problem here. The integral from 0 to x of f of t. So we're given that this integral is equal to the inverse tangent of e to the 3x. I want to find what the function f of x is. Okay, so if we are smart about this and don't get too stuck in our heads, it's really actually not hard to figure out. What could I do to this integral to get f of x?
I assume we don't do the thing we usually do, like just plugging in the x into.
Well, so here's the thing: to be able to plug in the x, you have to anti-differentiate.
Yeah.
But I don't know what it is. So
Hmm.
we were just talking about this moments ago. If you have the integral of a function and you just want the function, what can you do in front of the integral that gets you the function?
Oh, you just pretty much turn into a negative.
Not a negative. Right, so
you need to take the derivative.
Right, we can take the derivative. So that's kind of the trick here. If someone's saying, I'm giving you the integral of something and I want just the function, take the derivative of it. Right, the derivative of the integral from 0 to x of f of t dt. Well, if I'm differentiating this side, I also have to differentiate this side. But that's just f of x, which is what they're asking for. So we want to take the derivative of that. So the derivative of the inverse tangent of x is 1 over 1 plus x squared. The derivative of the inverse tangent of some stuff is 1 over 1 plus your stuff squared times the derivative of your stuff, which is 3e to the 3x. Or writing this a little more compactly, I would probably write this as 3e to the 3x divided by 1 plus e to the 6x, because e to the 3x squared, I multiply those powers together. Okay, questions about this?
Yeah, James, I'm a little confused. So I'm just confused and over the whole problem, to be honest.
So we're just using what were you okay with what we were doing just before this?
Yeah, like the things we've done before, easy, not even a problem.
So we're really doing the same thing, just kind of in a different context. So I'm looking at this and I'm saying, I want to find the function f of x. Okay, well, I know, and you know, you told me that, you know, you were totally cool what we were doing before. you know that the derivative of this integral is f of x, right? The derivative of the integral from 0 to x of a function of t dt, we're just plugging that x in there and we're getting f of x.
Yeah.
Okay, but here's the thing. They're telling us that this integral is equal to this function. So if this integral is equal to this function, and I want to find f of x, and I can find f of x by differentiating this integral, well, if this is equal to this, then the derivative of this is equal to the derivative of this.
Mm-hmm.
That's it, right? We're just saying, and this is always true, if two functions are equal, their derivatives also have to be equal.
The same.
Right. So I said, okay, the derivative of this is f of x, and the derivative of this, I'm just using my derivative rules to find it.
Oh, okay. Yes. Okay. Yes. I get it now. I
Cool.
completely get it.
Wait, James, a quick question.
Go ahead.
So for like our right side of our equation, we just take the derivative, right, of tan inverse, which is just, okay, yeah, that's predetermined already, so yeah.
Right.
Okay.
The derivative inverse tangent is 1 over 1 plus whatever's in there squared times the derivative of whatever's in there.
And so if we were asked to like find the antiderivative, what would we have? Yeah.
We don't have the tools to do that yet.
Oh, okay, okay.
It requires integration by parts. Some eventually we will get there, but not yet.
All right, sounds good, James. Thank you.
So one of the things I want to talk about was this this problem. This is from Morris's class. But my mouse good. Okay, I have. Oh, whoa! Stop doing that. Yeah. So the setup for this, I'm not going to go through the whole problem, but I am going to give you. I'm going to help you kind of get there. And I think this is due today. But let me kind of say a couple things. So the setup here is that the quantity N of T, so N of T, which is measured in kilograms of a pollutant that has leached from a toxic waste site after T days, is given by this interval. So N of T is the amount of pollutant. After T days. So let me just ask you conceptually, if N of T is the amount of something, what's the derivative? Like if I said N of T, or I'm trying to think of like a different context here. If I said the amount of distance I covered, right, was some integral, the derivative of that, I gave it away. No, I didn't. The derivative of my function is, well, in general, in fact, let's even not even look at this for a second. What does a derivative even mean? If I said you have the derivative of a function, I'm telling you about the what of that function. 3 words. First word starts with an R.
The rate of change.
Yeah, it's the rate of change.
Exactly. The derivative of a function is the rate of change of that function. So if N of T represents the amount of pollutant, then the derivative of N of T represents the rate of change of the amount of pollutant. So that's what, so now here's the thing. They don't ask you for M prime of T in this problem, but they do. What they actually ask you for is what is R of X? Or, although really they should have asked for R of T, but whatever, it's fine. So if I take this derivative here, everybody should be able to tell me what's the derivative of N of T. I want to see you type it in the chat or say words or something. Wait. Exactly, Katya. Yes, the derivative of the integral of this function is just the function, and it would be R of T. But they ask you what R of T means in this problem. Well, we just said it. R of t is the derivative, and the derivative we just said is the rate of change of whatever the function represents. In this case, the rate of change of the pollutant. So it's the rate of change of the pollutant in kilograms per days. Okay, they ask us a couple other questions. So notice I've graphed this thing even though they didn't tell us what the function was, because they told us two important things. They told us R of x was positive, meaning your function is always above the x-axis, and R prime of x is negative, meaning our function is decreasing. So this is a good enough guess at what the function looks like. So let's answer two more questions, or talk about two more questions. They're asking us, is n of t increasing or decreasing? Well, when you ask if a function is increasing or decreasing, you're really asking if its derivative is positive or negative. So let me ask everybody. Everybody should be able to tell me this question. Is the derivative positive or negative? Well, let's see. We know that the function r is given to be positive, but the derivative of n is r, so the derivative of n is positive. It's actually positive, Diana. So, right, they told us, right, so I want to be super explicit here. I'm not saying that you're correcting that the derivative of r is negative, but they're not asking us what the derivative of r. They're asking us, is n increasing or decreasing? So they're asking us, is the derivative of n positive or negative? And the derivative of n is equal to regular r, not r prime, just r. But we know that regular r is positive. So we know that n prime is positive, which means n is increasing. And in a similar way, we could ask about n being concave up or concave down. For n to be concave up, its second derivative has to be positive. Well, and I'm not going to spell this one out for you guys. I think you can handle it. Yeah, I think it means it's concave down, because n double prime would equal r prime. And we know that r prime, because it's told to us, is negative. Okay, here's the last thing I'll say about this problem. So there's this part C of this problem where it asks you to calculate a bunch of things. So let me draw some pictures for you, and then we're going to move on. So let's say here's 10, here's 20, and I want to space out a little more. 5, 10, 15, 20. So they ask you about a few things. They ask you what n of 20 is. Okay, well, there's n of 20. It's all that. It looks pretty big. They ask you what n of 10 is. N of 10 would be all that. And then they ask you for n of 20 minus n of 10. So n of 20 minus n of 10 would be all of this minus this, which is just that right there. Okay, let me ask you guys, which is bigger? N of 20 minus n of 10 or n of 10? Is this one bigger? And sorry, my colors are kind of backwards, right? I got my colors backwards here. Yeah, I blew it. Sorry. This one is that one. Let me erase here, Jaden. Apologies. You guys should already be able to answer the question though. Clearly, the region on the left or the right is the bigger one. Right. And the reason you're confidently able to say it's bigger is for two reasons. One, the function's decreasing, but just as importantly, two, they have the same base length, right? If this second part was longer, you would no longer be able to say for sure that this area was less than this area. but since they have the same base and this function is always higher than it is over here, this area has to be bigger. Okay, so then let's ask ourselves about the third part here. What if instead we were looking at the part in the middle, which is this part there? Well, I'm going to leave that to you guys. You can figure it out. I think you can get it, right? If you think about, yeah, I'm not even going to say anymore. I think you can get this. So, but I want to point out with that problem, it's really kind of important. And the teacher, the reason the teacher is asking this problem is they really, really, really want you to think about the context of this stuff, right? Yeah, we can take derivatives, we can use the fundamental theorem of calculus and do all kinds of calculations, but it's also important to understand the meaning, right? That when you're taking a derivative, you're just talking about a rate of change. Okay, let's see what else we got here. So I think I'm pretty much left with just definite integrals, U-substitution, area between curves. Only those three things. There's a lot of stuff, which we can all definitely talk about. Let's see here. I feel like I had some. There was that one. Oh yeah, and you guys had some questions. Let's see if I'm there yet. So let me just double check. So someone asked for 14 from Schulten's, which I think we're still not quite to yet. The question I have for myself really is, that was a pain. Let's calculate some definite intervals. Definite, yeah. So we can definitely do some definite intervals, and it depends kind of on. Yeah, are we just moving right into U-substitution already? Yeah, sure. Let's just like this. So I have an integral from 0 to pi over 2 of 4e to the x plus sine x. Okay. Sorry, just let me 1 second. I think I'm good. It's got a phone call. I just want to make sure it's not like important. I think we're good. Okay, yeah, that's you're not recommending. Okay, sorry. So definite integrals are you can say they're fairly straightforward. You're going to find the antiderivative. So the antiderivative for e to the x is 4e to the x. The antiderivative sine of x is negative cosine of x. And then you're going to evaluate between these two limits of integration. So we're just going to plug in. It's always the top limit first minus the bottom limit second. This is going to be 4e to the pi over 2 minus cosine of pi over 2 minus 4e to the 0 minus cosine of 0. And I do want you to be very careful. A lot of the time when we plug in 0, we get a bunch of zeros. That's actually not the case here. So here, 4e to the pi over 2, we just have to leave as is. There's nothing to be done. It's 4e to the pi over 2. Cosine of pi over 2 is 0 minus e to the 0 is 1. So you get 4 times 1 minus cosine of 0 is also 1. So you actually get 4e to the pi over 2 minus 3. And that would be this definite interval. I don't necessarily want to say the area under the curve because maybe this isn't always above the x-axis. It is always above the x-axis, but sometimes they aren't. But so in this case, right, your function, I don't know, your function maybe looks something kind of like this. Maybe it's wonky looking. And then we're just finding, and this is pi over 2, we're just finding the area under that curve by integrating it. Let's go ahead and look at a few more things. Yeah. So, right, a lot of our rules for anti-differentiation are still very much in play. So if I wanted to find, say, I don't know. Sorry, I keep covering up the chat here. One sec. So if I wanted to find, say, the integral from 1 to 4 of 1 plus the square root of x over the square root of x. Well, before I can do this, I need to simplify my integrand. I'm going to rewrite this as the integral from 1 to 4 of 1 divided by root x plus the square root of x divided by the square root of x. And that's just going to be the integral. Let's see, 1 over root x is x to the negative 1/2. And root x over root x is just 1. So now we're going to anti-differentiate. We're going to get, let's see. I should have done this differently. Oh, well, that's fine. So we're going to get x to the 1/2 divided by 1/2 plus x from 1 to 4. Or I would prefer to write this as 2 times the square root of x plus x from 1 to 4. And then we can plug in. We get 2 times the square root of 4 plus 4 minus 2 times the square root of 1 plus 1. Which ends up being, let's see, 2 times 2 is 4 plus 4 is 8. Minus 2 plus 1 is 3. You get 5. So definite integrals, a lot of the time, some of the time, are not too terrible. But you often have to manipulate them to simplify things, right? Let's look at this next example. The integral from 0 to pi over 3 of secant of x plus tangent of x. And again, please do interject if you have questions or comments or concerns about what's going on. Oh, sorry. Secant x plus tangent x squared. This one we definitely want to multiply it out. So multiplying this out, I get the integral from 0 to pi over 3. Something with something squared, you get the first thing squared plus the first thing times the second thing twice. So 2 times secant x tangent x plus tangent squared x. And 2 out of 3 of these things are really easy to anti-differentiate. What's the antiderivative of secant squared?
Tan x.
Right. What's the antiderivative of secant x times tangent of x?
2 secant x.
Right. But tangent squared is a little bit harder. There's a trick. And that trick is a trig identity. One of my favorite trig identities, actually. This one, which you might not have ever heard me say, but now you will never forget it. 1 plus tangent squared x equals secant squared x. Or as a student told me one time, I tan and get sexy. Impossible to forget. You'll never forget it. It's emblazoned in your brain. I tan and get sexy. 1 plus tangent squared x equals secant squared x. So we can replace tangent squared x with secant squared x minus 1. And then that's super easy to anti-differentiate. The antiderivative of secant squared x, we already did that as tangent x. And the antiderivative of 1 is x from 0 to pi over 3. Now, I would probably actually simplify this and say tangent of x plus tangent of x is just 2 tangent of x. That makes it a little bit nicer. And then the evaluating part. So here's the thing. If you've gotten this far, you've done all the calculus. The rest is just using your trigonometry or algebra skills to plug in these limits of integration and evaluate the thing. So if we plug in pi over 3, what's tangent of pi over 3? Well, in fact, if you don't know, I would suggest writing this. So write you're going to get 2 tangent of pi over 3 plus 2 secant of pi over 3 minus pi over 3 minus 2 tangent of 0 plus 2 secant of 0 minus 0. And if you do that, at least the person grading your will be like, well, they know what to do. They just don't know what tangent of pi over 3 is. But here's what it is. So tangent of pi over 3 is the square root of 3. Cosine of pi over 3 is 1/2. So secant of pi over 3 is the reciprocal, which is 2. And then pi over 3. Minus tangent of 0 is 0. Secant of 0 is 1. So you get minus 0 plus 2 minus 0, so you get minus 2. So simplifying this a little bit, you get 2 root 3 plus 4 minus 2 is plus 2 minus pi over 3. That's our answer. You will have to evaluate trig things sometimes. So yeah.
James, I have a quick question. Where did you get the negative x from?
So remember, right, tangent squared x became secant squared x minus 1.
Yeah.
The antiderivative of that was tangent of x minus x.
Oh yeah, of course. Yeah.
Wait, James, I have a good question as well.
Good.
So in our second line of the second line you wrote, after that, it's just that step is just like anti-differentiating, right? Or taking the antiderivative.
Sorry, this step here?
No, the one above it.
This step I was just multiplying it out.
Mm-hmm.
So if I'm still writing this symbol here, I haven't anti-differentiated yet.
Oh, that would
be expressed by integrand, right?
Okay. Yeah.
This that is your secant of x plus tangent of x 1 squared.
Oh, okay, yeah. And then the third line would be when we anti-differentiate.
Correct.
Oh, okay. Yeah.
James, I also have one more question. I'm not sure if where do you get these problems, like practice problems, from?
I make them up sometimes. I also use Grant's notes often.
Oh, for sure. So Grant has like a set of practice problems like on his website.
Yes, although these aren't the practice. So if you look at Grant's website, which I can definitely send everyone the link to right now, if you want to look at it, I am looking at the. So if you look at his website, in fact, I can share as well. I don't always use all of them exactly, but if you look at his website here, so like I'm looking at these integral properties note. I think I'm looking at these FTC notes actually, is what I was looking at, right?
Oh yeah, of course I see it. Yeah.
Right. Yeah. Exactly. That's what I'm looking at. But then if you look over to the left of that, there are problems. So there's a whole bunch of extra problems that you can, if you've got nothing better to do and you want more practice, lots of extra problems to work on. And then if you look back here, there's also solutions to them. So you're not just working blindly, right? You can actually go look at the answers later after you work on them.
Okay,
so yeah.
It's because I'm gonna have to leave early this class period because I'm gonna get my COVID vaccine. So
okay, good stuff.
Yeah.
So yeah. Also, I will definitely post the video so you can watch the rest of the video later.
Okay, of course. Thank you so much. I just I just don't want to miss it because I understand it, but why not get more practice in
More practice is always a good idea. So now the question I have to ask myself is, do we want to start talking about U-substitution more, or do we want to talk about area between curves? I'm kind of trying to think about which way the book goes first. Not that it really matters, but it kind of matters. Let's see. Oh, it's literally the same chapter. Substitution and area between curves. Okay then, fine. Fine then. Yeah, let's do area. We'll talk about area between curves, and then we'll talk about substitution, and then we'll talk more about area between curves. So, so typically, most of the time when we're dealing with area between curve stuff, it's usually going to be you're given a couple curves often, or maybe more, maybe 3, and you're asked to find the area bounded between them. Let's start off with a pretty typical example. Where'd you go, examples? I just had you up. Now I've lost my spot because I'm just going all over the place. It's all right. There we go. So let's say we want to find the area between these two functions. So the area bounded by, I might change this up just slightly. That's fine. Y equal to x squared minus 2x and y equal to 3x. And while I think it's definitely worthwhile to draw a picture for this, you do not have to draw a picture. So I'm going to do it without drawing a picture first, and then I'll draw a picture. No, I really think I changed my mind. I'm going to draw the picture because it is worthwhile to kind of have a physical interpretation. So y equal to x squared minus 2x is an upward opening parabola. It's got intercepts at 0 and at 2. It looks like this. I mean, really, to graph this nicely, it might be worthwhile to find where they intersect before I just graph away. Right? I know what this is supposed to look like, but I still might want to graph it. So if I set these equal to each other, and I subtract 3x, I get x squared minus 5x equal to 0. I get x times x minus 5 equal to 0. So I get x equal to 0 and x equal to 5. So that's where they intersect. They intersect at 0. So y equals 3x, right? It's going to hit this point here. And then they're going to intersect somewhere way over there. So I'm going to draw like this. So those are my points of intersection, 5, 15, and 0, 0. And I'm looking for this area here. And the idea is that just like before, when we found the area under a curve, we're still thinking about adding up rectangles. So I'm going to draw a little rectangle. I want to find the area of that rectangle. Well, the area of that rectangle is, just like before, the base times the width. It's the base times the width. And it's not the base, it's the height times the width, or the base times the height, right? Width, base, kind of thing. So it's the base times the height. The base is delta x, but since we're doing integrals, we're going to call it dx. So this base is a small change in x, dx, an infinitesimal change in x. The height, well, the height there is given by the difference in the functions. It's the top function minus the bottom function. So this is going to be, I kind of meant to write this in the other order, oh well. It's going to be dx times the top minus the bottom function. Okay, but then that's just the area of that one rectangle. I want to add up all the rectangles. I want this rectangle, I want that rectangle, I want all the rectangles. If I'm going to add up all the areas and then take the limit of that, I'm going to get the integral. So the total area is going to be the integral, or the adding up of all the rectangles from as far left as x equals 0 and as far right as x equals 5. And again, the area of each individual rectangle is the height times the base. So it's the top function minus the bottom function, which is 3x minus x squared minus 2x. You don't really need the parentheses there. Times the base, which is dx. That's how we find the area of this particular region. It's the integral of the top function minus the bottom function from their left point of intersection to their right point of intersection. Now, couple questions. If we didn't graph it, how would we know which function was on top? Well, I can pick, here's the thing. These functions intersect only at those 2 points, meaning they only change which one's on top or on bottom at those 2 points. So in between 0 and 5, they can't change which one's on top. So only one of them is on top. And we can find that by just testing any point between 0 and 5. So if I plug in, say, like x equal to 1, for this one, I get y equal to 1 minus 2. which is -1. And for this one, I get y equal to 3 times 1, which is 3. 3 is clearly bigger than -1. So this function, y equals 3x, is the one that's on top in that interval. Which is why we have 3x minus x squared minus 2x. So that's how you set this up. And then the calculation is the not as important, but still important part. So I'm going to simplify this just a little bit. I'm going to rewrite that as the integral from 0 to 5. 3x minus x squared minus and minus is plus 2x. So 3x plus 2x is 5x minus x squared. Then I'm going to anti-differentiate. I'm going to get 5x squared over 2 minus x cubed over 3 from 0 to 5. And we're going to plug in. I'm going to get 5 times 5 squared, which is 5 cubed, over 2 minus 5 cubed over 3. Here's a trick I've learned after doing this for a number of years. If you've got fractions and the numerator happens to be the same in both of those fractions, factor that numerator. Oh, sorry. I also forgot the 0. Minus 0 minus 0. But I can factor out a 5 to the third for both of these. And look at this. We get 5 to the third times 1/2 minus 1/3. To me, it just seems easier to subtract those fractions than it does to subtract those fractions. Right? Either way, your common denominator is going to be 6. But multiplying 125 by 3 seems a lot harder than multiplying 1 by 3. So I'm going to get 5 cubed, which is 125, times 3 sixths minus 2 sixths, which is 1/6. So I get 125 times 1/6, which is 125 over 6. Okay. That's not a good question to ask. So, area between curves. We find where they intersect, and then we kind of try and write an integral for them. So let's look at another example. And although you don't ever really, you don't usually have to draw a picture, I really do recommend drawing a picture. It's usually going to be a good idea to draw a picture of the region. It's just going to help you out. So let's look at this next one. I'm going to find the area between the following regions, or I have to say the area bounded by let's see, what have I got here? Y equal to 1 over x, y equal to x squared, and y equal to 9. And we could probably set this all equal to each other and find where they intersect, but I think it's going to be nicer if we just graph it. And yeah, and we're sticking to the first quadrant. Right, because 1 over x has some weird stuff over in quadrant 3. So graphing this, here's what the first quadrant part of 1 over x looks like. Here's what the first quadrant part of x squared looks like. There's also this part over here. And this one also has, right? 1 over x also has this part over here. And then y equals 9 looks like this. So it can actually be a little bit tricky to know which region you want. I've definitely seen people incorrectly say that this is the region. And you would not be super off base. I mean, you would be wrong, but you're not completely wrong in your thought process, because you say, well, look, James, that region has all the boundaries you mentioned. It has y equals x squared. It has y equals 1 over x. And it has y equals 9. And I would say you're correct, but it also has a region, a boundary I didn't mention. It has the y-axis, which is x equals 0. And that wasn't one of the boundaries I said. So that's not the region we want. This is actually the region we want. That region has y equals 9 as the boundary. It has y equals x squared as the boundary. And it also has y equals 1 over x as the boundary. And no other boundaries. So when someone says the region bounded by these functions, they specifically mean those functions and only those functions. You shouldn't have any extra boundaries. All right, so here's the deal. we're going to do what we did before, but there's an extra kind of twist. If I want to find the area of the rectangle, the vertical rectangle, well, vertical rectangles here have different heights or different functions bounding their heights. So if I look at, say, this rectangle, and let me just use a different color. Sure. Finger, never my favorite. So look at this rectangle here, right? That rectangle, its base is dx, and its height is the top function minus the bottom function, which is 9 minus 1 over x. And then this other rectangle, which I'll draw in black, over here, that rectangle has an area of, well, again, the base is dx, but the height is now 9 minus this lower function, which is x squared. So those are the areas of the rectangles. And again, I want to add up all the rectangles. So on the right side of whatever this point is, I'm going to add up all the rectangles to get that area where the height of the rectangle is 9 minus x squared. And in this region over here, I'm going to add up all the rectangles or the areas of the rectangles where the height of the rectangle is 9 minus 1 over x. So I have to set up two intervals. My total area is going to be this first integral, so this green one, of 9 minus 1 over x dx, and this second integral of 9 minus x squared dx. Now here's the thing. I need to find the limits of integration. So I need to find this point here, and this point here. All right, so this point here is where 1 over x and y equals 9 intersect. So I'm going to set these two equal to each other. We set 1 over x equal to 9, take the reciprocal of both sides, you get x equal to 1/9. So that point there is 1/9 common 9. So that, well, let's actually do the rest. This point here, you're going to get by setting 1 over x equal to x squared. Does anyone see an obvious answer to 1 over x equals x squared? Nobody? So oftentimes, oh, go ahead.
Would it be 1?
Yeah. So you're also, Diana, you're not wrong to think about x cubed, but it would be x cubed equal to 1. So yeah, you could totally do the work. So x cubed equal to 1. But a lot of times these problems are going to be designed in such a way that the place that they intersect is actually a pretty nice number. One of my favorite examples is a function where you're kind of trying to see where y equals 6 minus x and y equal to the square root of x intersect. And instead of like setting them equal to each other and squaring the whole thing and doing a whole bunch of work, you can just kind of guess the answer. Be like, oh, well, if I guess numbers are easy to take square roots of, 1 isn't right because square root of 1 is 1 and 6 minus 1 is 5. But 4 is right because square root of 4 is 2 and 6 minus 4 is 2. So sometimes if you guess kind of likely candidates, you can find the answer pretty easily. So that's this point here, 1, 1. And then finally over here, we're going to set y equals x squared equal to y equals 9. So set x squared equal to 9, you get plus or minus 3, right? Here's the minus 3 point there, but this point is 3, 9. So for this green region, we're starting as far left as x equal to 1/9, and we're going as far right as x equal to 1. For this black region here, we're starting as far left as x equal to 1, and we're going as far right as x equal to 3. So when I'm trying to find the area of a region, I'm typically, and I'm doing it in terms of x, I'm typically thinking of having vertical rectangles. I need to know the top and bottom of those rectangles. That tells me what I have, what minus what. And then I think about how far left and how far right those rectangles can slide. That gives me what my limits of integration are. let's go ahead and do this. Let's calculate it. And then we're going to do it again.
Wait, James, I have a good question.
Go ahead.
How did you figure out the last point of integration, the 3?
So I set this function.
Oh, x squared equal to 9.
Right, exactly. Let's see, calculating this, I'm going to get, so the antiderivative of this is going to be 9x minus the natural log of the absolute value of x, evaluated from 1/9 to 1, plus, integrating this, you get 9x minus x cubed over 3, evaluated from 1 to 3. So let's see what we get here. I'm kind of running out of room. I think I need to erase that picture. That's going to end up being, so this is going to be 9 minus natural log of 1 minus 9 times 1/9 is 1 minus natural log of 1/9. I didn't write the absolute values there because both my inputs were positive, so it didn't matter. Plus, plugging in 3 here, you're going to get 27 minus, plugging in 3 here, 27 over 3 is 9. Minus, plugging in 1, you can get 9 minus 1/3. Okay, I mean, it's not pretty, but it's something. So simplifying this just a little bit, natural log of 1 is 0. You end up with, let's go up here, 9 minus 1 plus natural log of 1/9 plus 18 minus 9 plus 1/3. So let's see, you get 9 minus 1 is 8 plus 18, plus, let's just call that 9. So you get 17 plus the natural log of 1/9 plus 1/3. Now let's leave it at that. Okay, we're going to do this one again. We're going to do it a different way. So often, when you are finding the area between some number of curves, and you have to do more than one integral, we're like, we don't want to do that. That seems terrible. And a lot of times, there's a way you don't have to do that.
Wait, James.
Go ahead.
Could you quickly switch back to the back part of the? Okay, thank you.
Well, so we're going to set this one up again, but now we're going to use horizontal rectangles. So here's my 1 over x. Here's my x squared. Here's my y equals 9. And now for this region, I'm going to use horizontal rectangles. Now, the main difference here is that instead of writing everything in terms of x, we have to write everything in terms of y. So the area of this rectangle, well, this rectangle has a base, it's dy, right? It's a small change in y, right? It's a small vertical change. So the base of my rectangle is dy, and the area of my rectangle is equal to, well, again, it's the height times the base, or maybe the length times the base is a better way of saying that. The base is just dy, and the length is, well, how do you find the length of this? Well, it's the bigger thing minus the smaller thing. So if you have a vertical rectangle, it's the top minus the bottom because y is bigger, higher, and smaller, lower. If you have a horizontal thing where we're integrating x as a function of y, x is bigger to the right and smaller to the left. So we need to do not the top minus the bottom, but the right function minus the left function. So my right function, well, my right function was y equals x squared, but again, we have to do things in terms of y because we're going to have a dy. So my total area is going to be the integral of some right function minus some left function dy. The right function is y equals x squared. We have to solve for x. So solving for x, you get x equal to, and I want to be extra careful here. It's actually x equal to plus or minus the square root of y. this side is x equal to the positive square root of y. This side over here is x equal to the negative square root of y. And that definitely does come up in one of your homework problems. That part of the when you have something parabolic and you solve for the other variable, you get the other variable equal to plus or minus the square root. And one side is the positive square root and one side is the negative square root. So our right function is the square root of y. And our left function is this function here, which is y equal to 1 over x. If I solve for x, so it's interesting, y equal to 1 over x, if you solve for x, you actually get the same function. Solving for x, if you multiply both sides by x and divide both sides by y, you get x equal to 1 over y. And now my limits of integration, well, if you recall, this point here was 1 comma 1, and this point here was 1/9 comma 9, and this point here was 3 comma 9. And we talk about how low and how high our rectangles can go. They can go as low as y equals 1, and they can go as high as y equals 9. Great, let's integrate this just to see it's actually the same. I'm going to rewrite the square root of y as y to the 1/2. So integrating this, we get y to the 3/2 divided by 3/2 is the same as multiplying by 2/3 minus the natural log of the absolute value of y from 1 to 9. Let's see what we get. We get 2/3 times 9 to the 3/2 minus the natural log of 9 minus 2/3 times 1 to the 3/2 minus the natural log of 1. Natural log of 1 is 0. So here's what we get. 9 to the 3/2 is the square root of 9, which is 3, cubed, which is 27, times 2/3 is 18, minus the natural log of 9, minus 2/3 times 1 to the 3/2 is just 2/3. I feel like my answer is off by 1/3. No, it's not. Here I have 17 plus 1/3, which is the same as 18 minus 2/3. And here I have plus natural log of 1/9, which is the same as minus natural log of 9. Right? Natural log of 1/9 is the natural log of 1 minus the natural log of 9. And that's just 0, so it's the negative natural log. So they're the same. And in most people's opinions, the second way of doing it is a more easy calculation. We didn't have to do, we only have to do one interval is really kind of the why people think that's easier. So
Wait, James, so just to like that last statement you just said, if we have like 3 functions intersecting one another, it's easier to like take it in terms of y because
what I'm really saying is it depends.
Mhm.
It totally depends on what the region is. Let me show you another example.
Oh, also James, for the one in the back, how did you decide that 9 would be our upper bound? Is it because we looked at the graph from right to left?
It's because so when your rectangles are horizontal, you want to ask how low and how high they can go.
Oh, I see. Yeah.
Low as y equals 1 and as high as y equals 2. Whereas with the previous problem, with vertical rectangles, we want to ask how far left, which is 1/9, and how far right they can go.
Okay.
Let's look at another one. So let's look at, I want to find the area of the region. I'll do my favorite problem. That's a good idea. Bounded by, sure, y equals 6 minus x, and x equals y squared. Yeah, this should work out all right. Okay. So let's draw it. X equals y squared is a parabola that opens to the right. And y equals 6 minus x is a line that goes down from left to right, has a y-intercept of 6 and an x-intercept of 6. So it probably looks something like that. So I'm looking at this region here. And so the question is, which way is it going to be easier to do this? Is it going to be easier to do it in terms of x, where I use vertical rectangles, or is it going to be easier to do it in terms of y, where I use horizontal rectangles? Well, here's kind of most people's deciding factor. Which one do I have to use less intervals for? Sometimes it's the same, or sometimes either way you do it, you only have to do one interval. But sometimes doing it one way means doing one interval, and doing it the other way means doing two intervals. And here it's definitely, if you do it using vertical rectangles, well, from 0 to whatever this point is here, the top function is this, the bottom function is this. From whatever this point is here to whatever this point is here, your top function is now something different. So this one will require two intervals. In fact, let's just set it up. I will say this is very similar, but not exactly the same to problem 14 that was asked about. So I still need to find the point of intersection. So I need to find where this and this intersect. And in this case, it's actually easiest to solve it by isolating x in both of them and then setting those equal to each other. So I'm going to write this one as y plus x equals 6, and then x equals 6 minus y. So I'm going to set this and this equal to each other. So y squared equals 6 minus y squared minus plus y minus 6 equals 0. This factors as y plus 3 times y minus 2. So you get y equal to negative 3 and y equal to positive 2. If y equals negative 3, x equals 9. So that's this point right here. If y equals 2, x equals 4. Okay. So one way to do this, one way to set this up using vertical rectangles, I would do this region here. So this first region, which the first region there, that's going to be the integral from, well, let's actually do the integrand part first. So the top function minus the bottom function. The top function is, the top function and the bottom function are the same. That seems wrong, because if you do the same function minus the same function, you're going to get 0. So here's the thing. This is where it's super important to recognize that the top function is y equal to the positive square root of x, and the bottom function is y equal to the negative square root of x. So when we do the top minus the bottom, it's the square root of x minus the negative square root of x, which you could totally say is 2 root x. The limits of integration are as far left as 0, as far right as 2. Plus, then we have to do this region here. Now the top function is this line, 6 minus x. And the bottom function is, again, the bottom part of this parabola, which is y equal to the negative square root of x. And my limits of integration, well, these rectangles can move as far left as x equal to 2, and as far right as x equal to 9. Great.
Wait, James, how did you decide that we wanted like y equals negative square root of x?
I didn't really decide. It's more that that's how it has to be, right? So I know that this rightward opening parabola is x equal to y squared. But if we solve for y, if we take the square root of both sides, well, you get the plus or minus the square root. This top part is y equal to the positive square root of x, because y is positive, right? If we're above the x-axis, you have positive y values. On the other hand, if you're down here, the y values are negative. So y has to equal the negative square root of x. If you plug in 9 for x, the square root of 9 is just 3. But this point is 9 negative 3. So you have y has to equal the negative square root of 9, which is the negative 3.
That makes sense. Thank you, James.
On the other hand, we could also do it just in terms of y. Like, hey, I want to use a horizontal rectangle instead. And the advantage of that is that the horizontal rectangle has the same function always on the right and the same function always on the left, right? Whereas the vertical rectangles, this region had a different top function than this region, which means we had to use two different intervals. So if we're using a horizontal rectangle, we only have to use one interval. So that integral, so again, the area of this rectangle is the width, which is dy, times the length, which is the right function minus the left function. The right function is this line, but we have to write it in terms of the variable y. Whatever your d whatever is, that's the variable you have to use. So the right function now is not y equals 6 minus x, it's x equals 6 minus y. Sorry, and that's the right function. That's the one. Sorry. So it's 6 minus y minus the left function, which is x equal to y squared. And the limits of integration are how low can your rectangles go? How high can your rectangles go? Or another way you could ask is, what's the lowest y value in your region? What's the highest y value in your region? The lowest y value in my region is -3. The highest y value in my region is +4. Same thing here, right? Here we went from what's the leftmost x value in our region? Oh, it's 0. What's the rightmost value in our region? It's 9. So we went from 0 to 2 and then 2 to 9. Okay. Let's do one more of these and then we will spend, oh man, time just flies by. At least I feel like it does. Hopefully you guys feel like it isn't just dragging on.
James,
Yeah.
if I may ask one last question for the back problem.
Sure.
The 6 minus y, it's top minus bottom.
Sorry, the x minus y.
Oh, for like when you wrote the integral of when we're using like y.
So that one over there.
Mm-hmm.
So when you're integrating with respect to y for area, not top minus bottom, it's right minus left.
Right minus left.
And so here's the way I'm really thinking about it. When you're integrating, so right, this here, this is x is some function of y. This here is x is some other function of y. So the reason you're doing right minus left is because you want to do the bigger x value, which is further right, minus the smaller x value, which is further left. On the other hand, when you do it in terms of x, well, this is y as a function of x. So the bigger function values are the higher y values, the smaller function values are the lower y values. So we do the bigger y values minus the lower y values, or the top minus the bottom.
Yeah, sorry about that. Okay, James, I think I understand.
Okay. We'll have lots more practice. So let's do one more. We might not really get to say much about U-Substitution today, but we'll have Thursday. So yeah. Let's see here. So let's say I'm just gonna set up. Also, be aware, a lot of times problems will ask you just to set something up as opposed to find the interval. So make sure you read your questions carefully. If something says just set it up, don't do more work than that. So I want to set up the integral, or integrals, plural, for the area between these two curves. F of x equals to x to the 4th plus 16x, and g of x equal to x to the 5th plus x to the 4th. So something worth noting about this particular problem is that you really couldn't do it in terms of y, or at least I couldn't, because there's no way we can really solve for x as a function of y. And a lot of, like in the previous problems, with both of these, you can totally isolate y, solve for it. But in this problem, both of these, you cannot really solve for y. It's kind of impossible. So that means we're kind of stuck doing things in terms of x. Okay, that's all right. Let's find where these intersect. So we're going to set f of x equal to g of x. So x to the fourth plus 16x equals x to the fifth plus x to the fourth. The x to the fourth cancel. We should not divide by x. We should say, okay, x to the fifth minus 16x equals 0. And then we should factor as much as possible. We can factor out an x. We're left with an x to the fourth minus 16. That definitely factors. That factors as x squared minus 4 times x squared plus 4. And that factors even further. That factors as x minus 2 times x plus 2 times x squared plus 4. So there are 3 points of intersection. X equal to 0, x equal to 2, x equal to negative 2. I don't know what this looks like, but here's the idea. We have, I'm not going to really draw this any particular way. I know that I have some function g of x that maybe looks like this. It probably doesn't actually look like that. And I have some other function f of x, which maybe looks like, like that. And they intersect at 0 and at 2. Oh, I forgot the negative 2. Ugh, blowing it. Let's just pretend like this is not 0 anymore. Let me fix this without really fixing it. Cool, that works. So let's say here's negative 2. And the idea is we want to find the area between these two curves. So between negative 2 and 0, we have to know which function is bigger. And between 0 and 2, we have to know which function is bigger. So we're going to pick a point in between. So I'm going to pick x equal to 1. And I'm going to look at f of 1 and g of 1. F of 1 is 1 plus 16. G of 1 is 1 plus 1. So for the interval from 0 to 2, I'm going to do f minus g because f is the bigger function. Okay, from negative 2 to 0, I'm going to test negative 1. So I test negative 1. If I plug in negative 1 here, I get 1 minus 16, which is negative 15. If I plug in negative 1 here, I get negative 1 plus 1, which is 0. So clearly, in this region from negative 2 to 0, g is the bigger function. So I'm going to do the integral from negative 2 to 0 of g minus f. So the setup for this would be, I'm going to do the integral, and we usually write the leftmost integral first. So I'm going to do the integral from negative 2 to 0 of g minus f. And by the way, this minus this is just x to the fifth minus 16x, right? The x to the fourths cancel out. And here's the nice thing. If you know what g minus f is, then f minus g is just the opposite of that. It's going to be negative x to the fifth plus 16x. Which makes sense, right? If you do f minus g, you get 16x plus x to the fourth minus x to the fifth minus x to the fourth, and the x to the fifth cancel, and you get 16x minus x to the fifth, or minus x to the fifth plus 16x. So that's how you would set this one up. And here, we're not going to do the rest of it because the problem said just to set it up. Okay, so let's go ahead and start talking about U-substitution for these last 15 minutes.
James, could you turn the whiteboard around really quickly? I have a good question for the integral from 0 to 2 negative x to the power of 5 to the power of 5. How come we made it into a negative?
because, so from 0 to 2, right, we're doing f minus g.
Mhm.
And if you do f minus g, it's this minus that. So f minus g, here, f minus g is x to the 4th plus 16x minus x to the 5th plus x to the 4th. And if you subtract that, you get x to the 4th plus 16x minus x to the 5th minus x to the 4th. Those cancel, and you can either write it as 16x minus x to the 5th or as minus x to the 5th plus 16x, which is what we have here. But what I really did was I said, I know that this one, f minus g, is x to the 5th minus 16x. And when you subtract something in the opposite order, it just becomes the negative of what it was. So if f minus g is equal to that, then g minus f, which is the subtraction in the opposite order, is just the negative of that, which is that.
Thank you, James.
Welcome. Let's talk about U-substitution for a few minutes here. So let's say I want to evaluate this integral. Sure, that's fine. Let's do the integral of 2x times x squared plus 6. And we're going to do it two ways. We're going to do it the easy way, where you can multiply it out. So you multiply this out, you're going to get the integral of 2x cubed plus 12x. And then anti-differentiating that, you're going to get 2x to the 4th over 4 plus 12x squared over 2 plus c, which is going to be, I'm going to simplify, x to the 4th over 2 plus 6x squared plus c. Great. But there's another way to do this. So the other way to do this is to say, well, I want to look for something whose derivative is also there. I'm going to say, I'm going to let u equal x squared plus 6. Why would I pick that? Because the derivative of that is also in my integral. Du dx happens to equal 2x, right? The derivative of that is definitely 2x. And then typically we multiply both sides by dx and we say that du is equal to 2x dx. So check it out. I'm going to rewrite this integral a little bit. I'm going to say it's the integral. I'm going to change the order of multiplication, which is totally allowed. Got x squared plus 6 times 2x dx. And this is my du. And this here is my u. So you can rewrite this as the integral of u du. We know how to integrate that. The integral of u is just u squared over 2, or the integral of your variable is your variable squared divided by 2. I'm just using the power rule. It's just a different letter of the alphabet. But then we should plug back in, not just should, we have to plug back in the variable starter, right? If you're integrating with respect to x and it's an indefinite interval, really that just says find the antiderivative. If you're integrating or anti-differentiating with respect to x, your answer should be a function of x. This is going to be u, which is x squared plus 6, quantity squared divided by 2 plus c. Are those the same? I don't know. Let's check it out. If you multiply x squared plus 6 squared, you get x to the 4th plus 6x squared plus 6x squared is 12x squared plus 36 all divided by 2 plus c. And then we simplify that a little bit further, dividing each thing by 2, you get x to the 4th over 2 plus 12x squared over 2 is 6x squared plus 36 over 2 is 18 plus c. Okay, let me ask you guys, are these the same? Yes or no? So I hear some yeses. And so here's what I would say. Both answers are really kind of correct. They're yes, they're the same, but no, they're not exactly the same. The answer I really should say is yes, they're the same enough. They differ by a constant, which is totally allowed for integrals, right? The integral of a function right? The antiderivative function, well, it's the same up to a constant, which actually really shows something important about integration. If you use a different method or technique of integration, sometimes your answer might be different by a constant. But yes, these answers are the same enough. This one is 18 more than that one, that's okay. So the thing is, sometimes you can't just multiply it out, or maybe you don't want to. For example, I want to find the integral of, I don't know, let's say x cubed times x to the 4th plus 1 to the 99th power. It is certainly technically possible. So here's the thing, Katie, if the integral was definite, it's a good question. So let's pretend the integral was definite for a second. And if we do it either way, let's see what happens. So first of all, when it's definite, you don't write the plus c. So you wouldn't have this. And let's pretend we're evaluating, I don't know, let's just say from 0 to 1. So here's the thing. I mean, so the short answer is yes, it's going to be the same. Exactly right. Right? You'll plug in the 1 here, and you'll get 1/2 plus 6 minus 0, which is 0. So you'll get 6.5. Here you'll plug in the 1 here, you'll get 1/2 plus 6 plus 18 minus 0 plus 0 plus 18, and the 18s cancel out. So yeah, doesn't matter, right? That's why it's perfectly okay to differ by a constant. Okay, so for this one, I was saying, it is possible to multiply x to the 4th plus 1 to the 99th power, but you should never, ever do that. It would take you quite a long time to multiply that all out. Instead, you should be like, okay, our u is x to the 4th plus 1. Why is that a good choice for you? 2 reasons. Reason 1, its derivative, or something that's a multiple of its derivative, is also in your integral. The derivative of u with respect to x is 4x cubed. And I have an x cubed, which is close enough. We can adjust for any constant multiples. The second reason why that's a good choice for you is because it's stuck inside some other function, right? Similarly, this integral, x cubed times sine of x to the 4th plus 1, we would make the same choice because, again, the derivative is showing up and x to the 4th plus 1 is stuck inside another function. Or this integral, x cubed times, say, e to the x to the 4th plus 1, and we would make the same choice because x to the 4th plus 1 is stuck inside the exponent, or stuck inside the function e to the something. So if you have a thing, an expression that is stuck inside a trig function, an exponential, a square root, the denominator, basically anywhere that's just not the usual place for something to be, or even stuck inside of something raised to a really big power, that is often the best, only choice for you. So then I need to do 2 things. I need to figure out how to make this work. So I have an x cubed dx. I want to make this look like I have x cubed dx on one side. So I'm going to multiply both sides by dx. So du is 4x cubed dx. And then I'm going to divide both sides by 4, or multiply by 1/4. So that 1/4 du is equal to x cubed dx. Great. X cubed dx is going to be 1/4 du. So then my integral is going to be, so I've got this part taken care of. I'm replacing that with 1/4 du. And then this part here is u to the 99th power. I should stress, when you're doing a U-substitution, it is absolutely vital, required, necessary, whatever you want to say, all of the x's have to become u's. Specifically, the dx has to change into something with du, typically a multiple of du. And then all the other x's also need to change. So this x cubed, right? This x cubed gets sucked up in, this x cubed times dx gets sucked up into the du, and then this x to the 4th plus 1 is just equal to u. And then we anti-differentiate. This is going to be u to the 100th power divided by 100 times 1/4 plus c, and then replacing u with what it's equal to, that's going to be x to the 4th plus 1 to the 100th power divided by 400 plus c. That's it. You can check this. You can take the derivative of this, right? Because the derivative of some stuff to the 100th power is 100 times your stuff to the 99th times the derivative of your stuff. So the derivative of that would be the 1 over 400. Let's put it down in front. The derivative of that would be 100 times your stuff to the 99th power times the derivative of your stuff. And look, that is exactly the same as that. Because the 100 times 4 and the 400 cancel out. Really what you're doing with the U-substitution is you're undoing the chain rule. Right? You're saying, I'm going to write this over here. You're saying f of x is, say, or f of u is u to the 99th power, and g of x is x to the 4th plus 1. And this looks like the integral of f of g of x, that's x plus 4 plus 1, u to the 99th, times g prime of x. And there's a 1/4. Literally, that's what this is, right? G of x is x to the 4th plus 1. F of something is something to the 99th. So that's your, erase this here. This is your x to the 4th plus 1 to the 99th power. G prime of x is 4x cubed. And then the 1/4 cancels out the 4 to give you x cubed. And then dx. So then we know, oh, that's the, oh, sorry. Yeah, sure. Yeah. Okay. So that's fine. So this ends up being f of g of x. Capital F, right? Where capital F is the antiderivative of little f. So that if you differentiate this, you get capital F prime of g of x times g prime of x. The capital F prime is the same as little f. Exactly that. So you're really just undoing the chain rule. You're saying, oh, I see the insides of a function is g of x. Its derivative is g prime. So you've got some f of g of x times g prime of x, and the antiderivative of that is capital F of g of x. Okay.